Welcome students to lecture number 8 on the MOOCs course on statistical inference. In the last lecture, we found that expectation of x bar is equal to mu, where x bar is the sample mean where the sample x 1 up to x n are from normal mu sigma square. Thus, sample mean is unbiased estimator of population mean. This we have seen. Obviously, the next question is, what is an unbiased estimator for sigma square? That is, we have taken sample x 1, x 2, x n, and based on that we want to find an unbiased estimate for the population variance sigma square. A natural guess will be sample variance. So, x 1, x 2, x n are my sample, x bar is the sample mean. Therefore, sigma x I minus x bar whole square upon n, that is the sample variance. The question is expectation of small square is equal to sigma square? Or in other words, whether the sample variance is an unbiased estimator for population variance. In order to find the answer, we have to compute the expected value of small square. Expected value of small square is equal to expected value of 1 by n sigma I is equal to 1 to n x I minus x bar whole square is equal to expected value of 1 by n summation I is equal to 1 to n x I square minus 2 x I x bar plus x bar square is equal to expected value of 1 by n into sigma x I square 1 to n minus 1 by n 2 x bar sigma x I plus 1 by n sigma x bar square 1 to n. This is equal to Therefore, expected value of this whole thing. So, this is equal to expected value of 1 by n sigma xi square minus expected value of 1 by n sigma xi is equal to x bar. Therefore, it is 2 x bar square plus 1 by n plus expected value of 1 by n into n x bar square is equal to expected value of 1 by n sigma xi square minus 2 times expected value of x bar square plus expected value of x bar square is equal to expected value of 1 by n sigma xi square minus expected value of x bar square. Now, we know that variance of xi is equal to expected value of xi minus expected value of xi whole square. So, variance of each xi is equal to expected value of xi square minus expected value of xi whole square is equal to expected value of xi square minus mu square, and variance of xi is equal to sigma square. Therefore, expected value of xi square is equal to sigma square plus mu square. By a similar logic, variance of x bar is equal to expected value of x bar square minus expected value of x bar whole square. And we know that variance of x bar is equal to sigma square by n. Therefore, sigma square by n is equal to expected value of x bar square minus mu square. Therefore, expected value of x bar square is equal to sigma square by n plus mu square. So, we find that 1 expected value of xi square is equal to sigma square plus mu square. 2 expected value of x bar square is equal to sigma square by n plus mu square. Now, we have already found that expectation of small a square is equal to this. Therefore, by putting these values, 1 by n summation over 1 to n sigma square plus mu square minus sigma square by n plus mu square is equal to sigma square plus mu square minus sigma square by n minus mu square is equal to sigma square into 1 minus 1 upon n. Thus, we find that expectation of small square is equal to sigma square into 1 minus 1 upon n is equal to sigma square into n minus 1 upon n. Therefore, small square is not unbiased for sigma square. Therefore, if I ask you what is an unbiased estimator for sigma square, small square is equal to 1 by n into sigma x I minus x bar whole square, I is equal to 1 to n is equal to sigma x I minus x bar whole square divided by n minus 1. So, that shows that our logical guess that sample variance is going to be an unbiased estimator for sigma square is not correct. The unbiased estimator for sigma square is this quantity, which is sigma x I minus x bar whole square upon n minus 1, and we often denote it by a square. Now, we want to find the distribution of or we can say we want to find the sampling distribution of capital A square. In order to do that, we first need some mathematical tricks. We have seen that when we transform from the xy plane to the zw plane such that z is equal to g1 of xy and w is equal to g2 of xy, we can get joint PDF of ZW as the joint distribution of xy expressed in ZW multiplied by the Jacobian, where the Jacobian is the determinant of del x del z del x del w del y del z and del y del w. Now, suppose we want to extend it to n dimension. The most important concept was that given ZW, we can use inverse transformation to get unique solution for x y. Now, we want to extend to n dimension. Suppose we write y1, y2, yn as a function of x1, x2, xn. So, we have n random variables x1, x2, xn. We want to make it transformation to new set of variables y1, y2, yn using a transformation function g. In particular, let us consider g to be linear transformation. That is, y1, y2, yn is equal to a times x1, x2, xn, where a is equal to a11, a12, a13, a1n, an1, an2, ann. We can get x1, x2, xn uniquely from y1, y2, yn. Let us use transpose notation for column vectors if A is invertible. Then we get x1, x2, xn is equal to A inverse y1, y2, yn. In this case, what is going to be the Jacobian? Let us write A inverse is equal to B is equal to B11, B12, B1n, Bn1, Bn2, Bnn. Therefore, x1, x2 up to xn is equal to B11 up to B1n, Bn1 up to Bnn times y1, y2, yn. Therefore, the Jacobian is equal to del x1 del y1 del x1 del y2 del xn del x1 del yn del xn del y1 del xn del y2 del xn del yn. Now, let us look at one of them. We have x1 is equal to b11 y1 plus b12 y2 plus b1n yn. Therefore, del x1 del y1 is equal to b11 del x1 del y2 is equal to b12 del x1 del yn is equal to b1n. Or in other words, the first row of the Jacobian matrix is going to be the first row of B. In a similar way, we can see that this Jacobian matrix J is nothing but the inverse matrix B. Therefore, the Jacobian of the transformation is equal to determinant of B, which is equal to determinant of A inverse, which is equal to 1 upon determinant of A. So, this is a very interesting observation. Now, in particular, suppose A is orthogonal, that is A transpose is equal to I. A is an n cross n orthogonal matrix. Therefore, A transpose is equal to identity matrix, or A inverse is equal to A transpose. Therefore, if we consider the transformation matrix to be orthogonal, we get this, and we also know that determinant of A is equal to 1. Therefore, joint PDF of y1, y2, yn is equal to joint PDF of x1, x2, xn multiplied by 1. This is expressed in yi's, right. Let us now consider x1, x2, xn as independent samples from normal mu sigma square. Therefore, f of x1, x2, xn, which is the joint PDF of x1, x2, xn, is equal to 1 over root over 2 pi sigma whole to the power n e to the power minus sigma xi minus mu whole square upon 2 sigma square is equal to 1 over root over 2 pi to the power n sigma to the power n e to the power minus half sigma xi minus mu upon sigma whole square summation I is equal to 1 to n. Now, let us consider the following orthogonal transformation. Y1 is equal to 1 over root n, 1 over root n, 1 over . So, y1 is considered to be the dot product of 1 over root n into x1 plus 1 over root n into x2 plus 1 over root n into xn. Let us consider y2 to be the second row is 1 upon root 2 minus 1 upon root 2 0 0. Therefore, first thing you note that the sum of squares of these values is equal to 1. Sum of squares of these values is equal to half plus half is equal to 1. Not only that, if we look at the dot product of this vector with this, we get 0. Therefore, these two vectors are mutually orthogonal. Similarly, we can have the third row is equal to 1 over root 6, 1 over root 6 minus 2 over root 6, rest are 0. Again, if you look at it, its sum of square is equal to 1 by 6 plus 1 by 6 plus 4 by 6 is equal to 1, and not only that, it is orthogonal to this and it is orthogonal to this. In general, the ith row of the transformation matrix is 1 over root I into I minus 1 into 1 1 1 I minus 1 times minus I minus 1 and rest are all zeros. Therefore, the sum square of the element is 1 upon I into I minus 1 plus 1 upon I into I minus 1 plus 1 upon I into I minus 1. This is I minus 1 times plus I minus 1 square upon I into I minus 1 is equal to 1 upon I plus I minus 1 upon I is equal to 1. Thus, the norm, the length of each of the rows of the matrix is 1. You can easily verify that its dot product with all the previous rows going to be 0. Thus, the matrix is an orthogonal matrix. Let us use this matrix for our calculation. Let y1, y2, yn be A into x1 minus mu upon sigma up to xn minus mu upon sigma. So, this A is the particular A that I have just constructed. Therefore, y1, y2, yn I can write it as A11 upon sigma, A12 upon sigma, A1n upon sigma, An1 upon sigma, An2 upon sigma, Ann upon sigma multiplied by x1 minus mu, x2 minus mu up to xn minus mu. This A1 is the original, these A1s are the matrix of the A transformation that we have considered. Therefore, its Jacobian is going to be one upon sigma to the power n, if I take the modulus. If I take 1 upon sigma to be out from each of the n columns, the determinant is equal to 1. Therefore, the mod of the Jacobian, if I consider this transformation, that is going to be 1 upon sigma to the power n. Therefore, if we consider the inverse of it, the Jacobian is going to be sigma power n. Therefore, joint PDF of y1, y2, yn is equal to 1 over root over 2 pi sigma to the power n into e to the power minus half sigma xi minus mu upon sigma whole square multiplied by sigma power n is equal to 1 over root over 2 pi whole to the power n e to the power minus half, and it is sigma xi minus mu upon sigma whole square, I is equal to 1 to n. Now, y1, y2, yn is equal to A times x1 minus mu upon sigma up to xn minus mu upon sigma. Therefore, y transpose y is equal to sigma yi square 1 to n is equal to x1 minus mu upon sigma xn minus mu upon sigma into A transpose A x1 minus mu upon sigma up to xn minus mu upon sigma is equal to, since this is equal to identity, is equal to sigma xi minus mu upon sigma whole square. Therefore, joint PDF of y1, y2, yn is equal to 1 over root over 2 pi whole to the power n e to the power minus half sigma yi square I is equal to 1 to n. What does it tell us? It tells that y1, y2, yn are IID independent identically distributed random variables such that each yi follow normal 0 1. So, the advantage of the particular transformation that I have made is that it converts from x1, x2, xn, each of which is normal mu sigma square, to y1, y2, yn which are independent and each yi is normal 0 1. Now, what is y1? y1 is equal to x1 minus mu upon root n sigma plus up to xn minus mu upon root n sigma. Is equal to 1 over root n sigma xi minus mu upon sigma is equal to 1 upon sigma root n sigma xi is equal to n times x bar minus n times mu is equal to root n upon sigma into x bar minus mu is equal to x bar minus mu upon sigma root n. And since y1 is normal 0 1, this is normal 0 1 as well. So, this also suggests that x bar is normal with mean is equal to mu and variance is equal to sigma over root n square is equal to sigma square by n. Although this result I have proved before, we can find it here also, but we get something extra. What is that? Let us consider sigma yi square 2 to n. This is equal to sigma yi square 1 to n minus y1 square is equal to sigma xi minus mu by sigma whole square I is equal to 1 to n, because we have seen some time back that sigma yi square is equal to sigma xi minus mu upon sigma whole square minus y1 square, which is equal to n upon sigma square into x bar minus mu whole square is equal to 1 upon sigma square into sigma xi minus mu whole square minus n into x bar minus mu square is equal to 1 by sigma square sigma xi square minus 2 mu sigma xi plus n mu square minus n x bar square plus 2 n mu x bar plus minus n mu square. So, it is n times x bar square plus 2 mu x bar minus n times mu square. So, this cancels is equal to 1 by sigma square into sigma xi square minus 2 mu sigma xi minus n x bar square plus 2 n mu x bar. Now, sigma xi is equal to n times x bar. So, this also cancels out is equal to 1 by sigma square into sigma xi square minus n times x bar square. On the other hand, sigma xi minus x bar whole square is equal to sigma xi square minus 2 x bar sigma xi plus n x bar square is equal to sigma xi square minus 2 n x bar square plus n x bar square is equal to sigma xi square minus n x bar square. So, these two terms are same. Therefore, we can write as sigma yi square from 2 to n, which we came out to be 1 by sigma square into sigma xi square minus n times x bar square is equal to 1 by sigma square into sigma xi minus x bar whole square. Now, 1 by n sigma xi minus x bar whole square is equal to a square. Therefore, sigma xi minus x bar whole square is equal to n times a square. Therefore, sigma yi square I is equal to 2 to n is equal to n a square upon sigma square. This gives us two important consequences. 1 n a square sigma square, which is same as n minus 1 into a square upon sigma square, is sum of square of n minus 1 independent normal 0 1 square, that is n a square upon sigma square is distributed as chi square with n minus 1 degrees of freedom, because n a square upon sigma square is sum of sigma y I square from 2 to n, that means n minus 1 of independent normal 0 1 square. Therefore, n a square upon sigma square is distributed at chi square with n minus 1 degrees of freedom. And the second point is that n a square upon sigma square is independent of y 1, because we have found that y 1, y 2, y n are n independent normal 0 1 variate, of which n square sigma square depends only on from y 2 to y n. Therefore, it is independent of y 1, which is nothing but x bar minus mu upon sigma by root n. Therefore, if x 1, x 2, x n are independent normal mu sigma square, then A x bar is normal with mean mu variance sigma square by n, B sigma x I minus x bar whole square upon sigma square is distributed as chi square with n minus 1 degrees of freedom, and C distribution of x bar and a square are independent. So, these are three important findings that we get by making a particular orthogonal transformation of x 1, x 2, x n to y 1, y 2, y n. So, these are some important results that we obtain when x 1, x 2, x n are independent samples from normal mu sigma square. With that, I stop for today. Thank you.